that is represented here. Now this is an equivalent finite state automata diagram, so a finite state machine. This is how state charts represent it. This is how you would have to do that. Let's look at that in a little bit more detail. So here's a simple example of concurrency, where we have a state machine here in state A, which just consists of two states and two non-trivial transitions in A, and then B, same thing, two states, but now there are three non-trivial transitions. So one of the benefits here is that this is why this is much simpler and easier to understand than this, because we get this state multiplicity, right? So this is illustrating actually two things, right? The concurrency is these finite state machines are independent, but there is a tie between the events on this acting on this state machine and the events acting on this finite state machine. So if you're in event C, and again these are concurrent, so we might also be in event E, or I'm sorry, in state E over in this machine. So the system is in state CE, because on one state machine you're in state C, and the other state machine you're in state E. When you're in C and you get the X transition to D, it also triggers the Y. And Y, you see, appears here between the E and the F in the concurrent running state machine. So again, there's synchronization between these in that event X can trigger event Y. And these can then be in different state machines, and they get processed, then they have the effect on both, right? A single event X will cause C to transition to D, but that'll generate a Y transition, which only appears in here. And if you're in state E, now you would be down to one option there to translate. Now, so now note so if we note with a state machine with two states and a second state machine with two states, now you have compound states, which would be two possibilities, right? You could be in state C or D and could be simultaneously in state E or F. And so that's what we see here, is there's CE, CF, DE, DF. Those are all the combinations. And you can see that even with this very simple, there are only four states, two groups of two. This one is 4 states and 5 transitions. This is 4 states and a total of 8 transitions. And again, it just seems a lot more muddled, this finite state automata diagram, finite state machine, because you're trying to represent. So this is a more compact and easier to read operation. You know these things are going concurrently because you see the concurrency bar, and we have synchronization across the events, that if X happens, then that's going to trigger Y, and then Y, if you happen to be sitting in state E here, then you would, with Y, transition to F. Now, if you're already in F, so suppose you're in C and F and you get an X event. Again, C is going to transition to D, but the X is going to cause a Y, but a Y doesn't do anything over here, so it's going to stay in F. So you will essentially move from CF to DF. What are the problems with state charts? LaPlante has this rosy text that, hey, state charts are excellent for representing real-time systems because of the concurrency, the modularity, you have this broadcast communication, it's easy intertask communication representation, etc., etc. Wouldn't that be nice? Okay, there are some problems with state charts. One thing is using concurrency and synchronization, a couple of those things that LaPlante says are wonderful, right? And they are. Here you can get infinite loops. You can see in this example, this is a valid representation of these two concurrent states. You have state A represented by substates C and D, state B represented by substates E and F, and notice that X causes a transition back and forth and triggers a Y. And likewise, this is reverse. So Y is the primary trigger for the transition, and X is caused as a result. So imagine you're in state C and E. So you get an event X, you're going to transition over here, but that's going to cause an event Y, which is going to transition you over here. But transition Y causes an X event, which if you're now over here, you're going to transition back to C, but also cause a Y event. So this one is going to transition back to E, which causes an X event, which is going to transition you back to D, which causes a Y event, which is going to transition you back to F, etc. So you can, in fact, have these infinite loops. And that's a legitimate, but of course you can have infinite loops in C, right? And that's the thing, is it's an unfortunate side effect. Now, there is also some non-determinism here. Imagine you have similar situation, two states A and B, each consisting of two substates, but now the question here, and there are in fact two questions on determinism. Let's assume you're in C, in state C and state F, and you get event X comes in. Well, depending if you evaluate B first or A first, you can get different behavior. So if we evaluate A first, then C is going to take X, it's going to transition to D, causing a Y, and the X is going to cause a transition here into from F into E, right? And then you have, of course, there is the state Y, which is triggered by that transition into D, which has no effect on this state machine, but this one transitioning to E causes an event C, which then this one can retransition back into C. If you do it the other way, then you won't get that. Likewise, you can say, well, wait a minute, just within, not just on which side do you transition, but if you start over here and again the X event comes in, you transition to D, causing a Y, and then you were here, there was an X transition, and it would end up in E. Okay. Now, there's also a non-determinism that can result from hierarchy. So here is a case where you enter the root, you go into the off, and so you're in the off state. If you get an on command, you're going to move into here, which is your initial entry into on means you're going to go into B. But then that's going to cause an X transition, which sends you directly into D. So effectively, then, are you transitioning directly into D, or is this an intermediate state, basically, that you're in B and then you transition into D? Now, so the bottom line is there are some problems that are generated through the concurrency, synchronization, and hierarchy. But they are still useful for real-time and embedded system specification because they are a formal method. You can prove aspects of system operation based on this, and they directly convert into code so that the simulation can be the executable as well. Um, it's a graphical notation. It can be cluttered, and but it's specific, modulo some of these non-determinisms that we've talked about. But there's still a need often for textual notation. And remember, we talked about things like natural language specification that should go with your state chart specification. Now, there are these problems we talked about, loops, dependencies, that sort of thing. And this idea of broadcast event mechanism, right, is a potential breaker to modularity. But the good news is there's a fair amount of community support. There's a state chart GitHub repository. There is also state charts are commonly used in Unified Modeling Language, UML. So this is so there's a tool actually here that talks about how to create those state diagrams. But it's versatile, and UML, the Unified Modeling Language, is also a good language for modeling entire systems. And then finally, I mentioned at the beginning the iLogix Rhapsody that is now maintained by IBM. There's also the Yakindu state chart tool, the SCT, which is an open source, and now it has gone closed source actually also, very similar to the way StateMade evolved into Rhapsody. But as of version 3.0, Yakindu now is proprietary, but is available for free to academic institutions.